Hello students, today we are going to see effect of neutral disconnection in a three-phase four-wire system. To analyze the effect of neutral disconnection in a three-phase four-wire unbalanced star-connected load using SCI LAB. For the doing of this experiment, we are going to use a SCI LAB software. Problem statement. The goal of this experiment is to find out the phase currents with the neutral connected. So first we are connecting with the neutral. What is the phase currents? Then determining the floating neutral shift voltage when the neutral is disconnected. When the neutral was disconnected, the neutral voltage was floating. That voltage also we are going to calculate. Next, calculate the new phase voltages and the currents. That is the new phase voltages and the currents because of the neutral is disconnected, and the analyze the imbalance condition by using the SCI LAB. So algorithm for this program. So just open the SCI note, then select a new file and enter the code, save the file name, get the input from the user input. So whatever we can give the input, but here defaultly we are giving some values while taking the problem only, and assign it to the proper variables. In the program we are going to assign it to the proper variables. Next, apply appropriate equation to solve the problem statement. That means from the theory part we are going to solve. Next is use a printf or display to display the print results. So given data, all these things we will do by using the calculations that I will explain in the image here. So this is the problem statement. What we have given: a three-phase four-wire supply has a phase voltage of 230 volts with floating unbalanced load impedances. ZR value, that is R impedance, is 20 ohms, Y impedance is 30 ohms, ZB is 15 ohms. Performance of the following: calculate the phase currents when the neutral is connected. When the neutral is disconnected, we are going to compute all these things, that is a neutral shift as well as the new phase voltages across each load and new phase currents. So and finally we are going to compare the results. Now see, the value of R phase, that is the voltage across the R phase value, I have taken it as 230 volts at an angle of 0 degrees, that is a reference voltage. Next, Y phase is 230 at an angle of minus 120 because it is lagging by 120 degrees. B phase is 230 at an angle of 120, it is leading by 120. And the impedance which is connected in the R phase is 20 ohms, Y phase is 30 ohms, and B phase is 15 ohms. Let us calculate the phase currents when the neutral is connected. IR value is equal to, we are going to calculate it by VR divided by ZR. That is from the Ohm's law, V divided by Z. 230 divided by 20. So the answer you are going to get is 11.5 amperes. Next, the phase current in Y phase is equal to, that is 230 at an angle of minus 120 divided by 30. We are going to get 7.67 at an angle of minus 120. This is a polar form. When you convert it into rectangular form, you are going to get minus 3.83 minus 6.63 I. This is a rectangular form and this is the polar form. This will represent the magnitude here. So the magnitude of phase current Y is 7.67. Next, the phase current in B phase is 230 at an angle of minus 120 degrees divided by 15. So when you divide that, 15.33 at an angle of 120 degrees you are going to get. This is a polar form, and in the rectangular form minus 7.66 plus 13.27 I. Neutral disconnection. So now we are going to check, these are all the values when the neutral is connected in the star connection. Now we are going to disconnect the neutral. Because of that, what is happened? So the neutral is not going to constant, it is going to variable, or it is going to in floating condition. So this you can observe. If you want to go for theoretical or any derivation, you can observe a three-phase four-wire unbalanced system in ECA subject, whatever you have studied in the lower classes. The floating neutral voltage is Vn dash is calculated by VR by ZR, Vy by Zy, Vb by ZB divided by 1 by ZR plus 1 by ZY plus 1 by ZB. This is a formula we are going to calculate for the floating neutral condition. That is, if you substitute all the values, then you are going to get 44.22 I. So I means here it is 1 at an angle 90 degrees, that is a imaginary number, 44.22 at an angle of 90 degrees. Now new phase voltages will be calculated by, so when the neutral is open, that is the neutral is disconnected. So how we are going to calculate is, we should subtract, that is a VR new we should subtract from this old one. That is what is the value we have taken for the neutral voltage, sorry, R phase voltage is 230 at an angle of 0 degrees. That you subtract minus 44.22 at an angle of 90. So you subtract from all the phase voltages, that is Vy 230 at an angle of minus 120 minus 44.22 at an angle of 90 degrees, Vb minus Vn, that is 230 at an angle of 120 minus 44.22 at an angle of 90 degrees. So that you are going to get the new phase voltages you are going to get here. After getting this new phase voltages, so the value you are going to get the subtraction, that is the value just I have taken here magnitude, that is 234.22, here is I. Next is Vy value you are going to get 269.24. If you observe here, whenever you subtract, the values will be increased here. So the magnitude we are calculating here, 230 at an angle of 230 minus 44.22 I is a rectangular form, and if you take a polar form you will get this magnitude. Rectangular to polar conversion you can do in the calculator also. 234.22 volts. Vy value, new value is, actually this is in the rectangular form, the polar form is 269.24, that is the magnitude is increased, and Vb value is also will be increased from the previous one. So what will happens, that is IR new, that is the phase new currents value will be VR divided by ZR, that is the VR new value we got it as 230 minus 44.22 I divided by 20, then you will get a rectangular form, the magnitude is 11.71. Next Iy value is Vy divided by Zy, the value is here is this one. So minus 115 you substitute from here, so that you substitute here, then you are going to get by 30 divided by 30, the value is here is 8.97. Ib value here is how much you are going to get, Vr divided, that is Vb new divided by Zb, this value substitute divided by 15, then you are going to get 12.86. So the values if you observe clearly from the previous one and this one, just I want to show the previous values. What are the previous values we got here? 11.75 here and minus 3 point, that is the magnitude is 7.67, here 15.33. But if you observe, the values here is increased. So previously 11.4, 11.5, now it is increased to 11.71. Previously it was only 7.67, now it is increased to 8.87. Previously it was, the value of this current is 15.33, now the value here is increased to, the values are increased 12.86. the values will be increases here in the two phases. So here one phase is decreased, actually 15.33 here is value is high, but whereas here it is decreased. So if you observe, there is an imbalance will be there in this connection. So there is a imbalance will be there, you can observe when the neutral is disconnected. That's why always we are going to connect the neutral connection will be there in the for this. So these calculations I have done in a code. Now the SCI LAB code I am going to explain here. So this, if you type all the same thing in the SCI LAB, then you are going to get the values are executed. So VR value we are taking it as 230 at an angle of 0 degrees. So at an angle it is not represented here, just it is marked as a question mark when copying. Next Vy value is 230. So that is we are going to write percentage I 120 percentage pi, that is a percentage I is indicates the, that is at an angle, that is we are going to represent as 230 at an angle of 120. Whenever you write in the exponential form of the rectangular number e to the power of minus I theta or e to the power of I theta, so that it is going to represent here. So angle is 120, that is e to the power of minus I theta. So that is a imaginary number. So for that imaginary number we are taking the percentage I, percentage pi divided by 180 degrees. Next VB value is 230, the same thing exponential, only thing is here we are changing this plus I, that is a e to the power of plus I theta, here it is e to the power of minus I theta. So that is another representation of rectangular numbers. ZR value is 20, ZY value is 30, ZB value is 15 degrees. Now we are going to calculate the currents with the neutral connected. The formulas are IR is equal to VR divided by ZR, IY is equal to VY divided by ZB, IB is equal to VB divided by ZB. Just displaying that. So display currents with the neutral connected. Display value IR is equal to these values will be displayed from this calculated values. Once the program executed, you will understand all these things what are that is going to display. Now the second case we are considering here is floating the neutral voltage, that is when the neutral is disconnected. When the neutral is disconnected, we are going to use all these formulas here. So what are the formulas? That is same formulas only when the neutral was connected. Now we are also going to use the neutral is disconnected. First we should calculate the VR value, that is a floating neutral voltage. For that, the numerator is VR divided by ZR, VY divided by ZY, VB divided by ZB, and the denominator is 1 by ZR plus 1 by ZY plus 1 by ZB. So now Vn will be calculated by numerator divided by denominator, that is a neutral shift voltage. So just I have displayed the neutral shift voltage, and the magnitude also we are taking the magnitude of Vn. So absolute value, so V absolute value will gives us the exactly what is the magnitude of neutral shift voltage. Now new phase voltage are across the load. When the floating was neutral was floating, now we are going to calculate the new phase voltages, that is VR new is equal to VR minus Vn, VR new is equal to VY minus Vn, VB new is equal to VB minus Vn. So just you subtract the neutral floating voltage from the previous voltages what you got, then you are going to get the new phase voltages here because of the neutral is floating. Now you display that values, display neutral new phase voltages after neutral disconnection. So that is we are going to display the values and display the magnitudes also. First you are going to get the rectangular number, just I want to display the magnitude also, that it is going to display here. After that, now the new load currents, the new load currents how you are going to get, that is VR new divided by ZR, VY new divided by ZY, VB new divided by ZB, the new currents after neutral disconnection, that I want to display here, and the magnitude also I am going to display. Just I am showing the output here what it is going to get whenever you are executed in the SCI LAB software. So IR value you are going to get 11.5, IY value here you are going to get is minus 3.83 minus 6.63, IB value is minus 7.66 plus 13.27. These are the values when the neutral is connected. Now when the neutral is disconnected, this is the values. First we are going to calculate the neutral shift voltage. The neutral shift voltage, whenever you calculate that in rectangular form, you are going to get this in the magnitude form, the 44.26, that is in total magnitude of this rectangular number. Next is when new phase voltages, that is a new phase voltages means how you are going to get, you subtract from the 230 at an angle of 0 minus this one, then you are going to get the VR new. Same thing here, VY new you are going to get here, VB new also you are going to get. Just I have given the magnitudes of this, that is a VR new magnitude is how much, 234.224, VY new magnitude is 269.24, VB new magnitude is 192.94. new currents, that is we are going to calculate after the neutral disconnection. So when the neutral is disconnected, what will happen? IR new value will be how you are going to get, that is VR new divided by ZR. So whenever you subtract VR new divided by ZR 11.5, that you are going to get. Next is IY new value is this one, IB new value is this one, and the magnitude you can observe. Previously 11.5 was there, now it is increased to 11.7. Previously how much here? Previously how much value here? IB value something approximately 7 point something. So, but here it is increased to, now you can observe the IB value is increased to, sorry, IY value is increased to 8.97. IB value it was previously 15 point something, now it was decreased. So you can observe there is some imbalance will be there whenever, because the neutral is floating here, the values are here will be you can observe here. So first of all you understand the theoretical calculations what we are explained in this video, then you can go for this problem understanding, that is a program understanding in the SciLab. Let us go for the SciLab atmosphere. Now what we are going to see. See first you can see this screen appearance whenever you enter into the SciLab execution. Then you enter as editor. So first you enter it as editor, then you can go for enter. So directly it will go, because I already saved the program, directly it is going. Otherwise a blank screen will be open here like this. So actually a blank screen will be open like this, then you enter the program whatever I have given, just you save and execute. So the program name to be I have given it as effect of neutral, then save and execute, or you can execute directly, then you can go for execute. Once you execute, the values will be displayed directly here, the values are displayed here directly. So what you can observe, currents with the neutral is connected. So currents is neutral is connected, 11.5 IY value is given and IB values are given. First the value is displayed, then the name of that value is, the variable is assigned, you are going to get displayed. Then after that neutral shift voltage you are going to get, the neutral shift voltage is Vn value, how much value you are going to get here, that is we are already shown. Magnitude of that we are going to calculate as 44.26. Now the new phase voltages after neutral disconnection. So after neutral disconnection what you are going to get, just I will close that so that you can clearly you can observe whatever we are seeing here. So neutral phase voltages after disconnection, that is a VR value, that is 230 minus something. Next VY value you are going to get this value, VB value you are going to get this value. For these rectangular numbers I have taken the magnitudes here, 234, next 269, here 192. Next is after this change of this neutral shift voltage, then we are going to get the new currents after neutral disconnection. How we are going to get? Whenever you divide this, that is the new magnitudes, that is 234.22 divided by ZR value is 20 approximately 20. So ZR divided by 20 divided by this value divided by 20, you are going to get this value. Next is Vy new, that is a rectangular form. If you take this divided by 30, you are going to get this Iy new value. Next Vb new value is minus 115.114 divided by just 15, then you are going to get the IB new value. And for this magnitude if you take the magnitude also will be displayed here, this magnitude is increased, this magnitude is also increased, whereas this magnitude is decreased. So you can observe there is an imbalanced condition when the neutral was disconnected, so which is avoidable whenever we are doing a three-phase forward system distribution system. So I think so this video was helpful for you. So if any doubts or clarifications you want, you can contact me. Thank you very much.